this video, I'll talk about the log spiral theory, which is very commonly used for passive earth pressure problems, just because the assumption of a planar failure surface is wrong. And so what we'll do is first talk a little bit about the log spiral. And if we go all the way back to shallow foundation bearing capacity theory, you may recall that there's three different distinct zones beneath a footing, and this would have a symmetric failure surface to the other direction for uniform soil properties. We have zone 1, which is an active zone, and the reason it's called active is that the vertical pressure is bigger than the horizontal pressure in zone 1. You may be thinking, why is that active? Active earth pressure happens when a retaining wall moves away from the backfill. Well, active failure actually is any time when the vertical pressure is bigger than the horizontal. Zone 2 was the zone of radial shear, and it was non-triangular, right? It has this curved surface on the bottom. Well, that curved surface is a log spiral. And the property of the log spiral is that there's a normal force and a shear force, and the resultant of that normal and shear force always go through the center of the log spiral. So basically the radius is increasing as the angle increases for that log spiral. It's defined in polar coordinate space. And then zone 3 over here is a passive zone. And again, that may seem weird. Why is that a passive zone? Well, this footing is pushing down and generating horizontal pressure. And so in zone 3, the horizontal pressure is actually bigger than vertical, which is why it's a passive zone. So that log spiral property for foundation bearing capacity is not something new, right? We've already been through that before, and so it's not a surprise to us that a log spiral also exists for retaining walls. So here, let's do active pressure first. This little dashed line that I've drawn there for a retaining wall might be the planar failure surface that we've assumed for Rankine and Coulomb earth pressure theory. Well, the log spiral failure mechanism is probably pretty close to that, maybe something like this, right? So that would be the log spiral. And as a result, the earth pressure that you get from the planar failure surface is actually pretty accurate. You will get a slightly higher earth pressure from this log spiral, but it's so close. They're just so close together that we often do use planar rupture surfaces to determine active pressure using Coulomb or Rankine earth pressure theory. Okay, when we come over to the passive case now, recall that the direction of the failure surface at the wall interface really depends on the direction of the earth pressure resultant. So in this case, our earth pressure resultant was acting upward on the wall because the soil is settling relative to the wall. Therefore, the wall must be pushing up on the soil. It's the opposite here. We would have the wall actually pushing down on the soil, because as you push the wall into the backfill settles up, and so therefore the interface friction is mobilized in the other direction. And as a result, the launch angle here is downward, right? So as this one was upward, this one is downward, and it follows a log spiral and maybe comes up like that. And this is just schematic. I'm not saying that they end necessarily at close to the same point there. But anyway, you see that these failure mechanisms are really quite different, right? This planar failure surface really is the wrong one. And this one will give you a lower passive pressure. So it's a better estimate of passive pressure. Great. So how do we come up with the properties of this surface now and the equilibrium conditions? Well, I'll show you some tables that have earth pressure coefficients summarized. It turns out it's not so easy to just conveniently come up with a simple expression anymore for passive earth pressure, so a lot of the time we pick out values from a table. I will mention that you can use procedures of slices. Jumped ahead there a little bit. So, you could come into your slope stability software and impose some loading condition here and divide your mass into a bunch of slices. And then, for each slice, you're going to have to make assumptions about interslice forces, use a method that satisfies equilibrium. You don't want to use the ordinary method of slices or the Bishop simplified procedure here. This should be something like Spencer's method or Morgenstern and Price. So anyway, that's always an option, and you could use a kind of a curved failure surface or some kind of a path search or something like that to get your passive pressure. All right, the other way to go is to use something like this table of values. This is from the NAVFAC design manual. So this is a Navy document, version 7.02 is showing here. And this table, let me zoom out on it so you can kind of see the whole thing, and then we can zoom in on different parts. This table has passive earth pressures here, kind of above this 1.0 line, and active earth pressures down here below the 1.0 line. So it's really a kind of sort of a fully formed table where you can do both passive and active pressures. You can check this, but if you come out here to some typical friction angle, 30-something degrees, you're going to get a result that's very similar to the planar rupture surface if you do the active coefficients. What we're going to use this for primarily are the lines up here. These are the passive lines. Okay, and so there's actually two versions of this table that I'll provide. One of them has a horizontal backfill, that's this one, with a passive failure, and a wall inclination angle that varies, right? The second one down here has an inclined backfill and a vertical wall. There isn't a table in this manual that has both wall inclination and backfill inclination together, so you may have to do some judgment call or some interpolation here if you have that condition with both a sloping wall and a sloping backfill. So the way that you would use this is the x-axis is internal friction angle. So it goes all the way from 0 up to 45 degrees, which should cover us for the range of friction angles that we'll commonly use in design. Common number might be 30 degrees or 32 degrees or something like that. Then, okay, they're using theta here. I used alpha before, and they're actually using a value of theta such that theta is 0 if the wall is vertical. So this line up there is for a vertical wall with a horizontal backfill. And so that line is duplicated on the next plot also. And then these other lines are just for different angles of wall inclination. Note the sign convention here, a positive angle up here, like let's see, plus 10 degrees, plus 20, plus 30, and so forth would be if the wall is sloping that way. You might have negative angles too, where the wall's sloping the other direction as you push into the soil. Most commonly, you're going to have positive angles or 0 angle. So you would come up here and pick off a number, like if our friction angle is 32 degrees, it's there. We would come up along this line to this point, which is our earth pressure point, and then we would come across here, and so we can see our Kp value is maybe about 7.8 or 7.9 in this case. Okay, and that by default is for a condition with delta equals phi. All right, and then there's this table up here of reduction factors that get applied if delta is less than phi. So let's say we had that case where delta over phi is 2/3. We would have to come here. See, here's delta over phi in these numbers. We would be somewhere close to 0.7. So maybe we would come down here and apply a reduction factor of 0.878 in this case. So our passive pressure is reduced by a factor of 0.878 if our wall to soil friction angle is 0.7 times phi. So anyway, that's how we would end up getting Kp for that plot. So it's pretty straightforward and easy. Okay, one thing is that this is giving you the actual inclined resultant force, right? So P sub P is shown here. It's inclined at an angle. It's Kp gamma h squared over 2, where the Kp is picked off of this plot. A lot of the time what we want to design for is actually the horizontal component, right? So Pn would be the normal component to the wall, Pp times cosine of delta. If the wall is vertical, then that's the horizontal component. If the wall's not vertical, you'd have to do another transformation to get that as well. And then Pt is the transverse or the shear force acting between the soil and the wall. So it's good that the table has this because it's not always clear whether that cosine delta term is factored in or not. It's not factored in here. If you want horizontal pressure, you have to apply it later to get that horizontal component. All right, same thing here. This is basically the same table, except now the different numbers are for beta over phi, where beta is the the backfill inclination angle. Positive would be upward slope like this, which will tend to increase your passive pressure. Negative would be downward, which would decrease your passive pressure just because the length of the failure surface becomes less. So pretty straightforward. Okay, then the last thing that I'll talk about here is design earth pressures or equivalent fluid unit weights. And this is a table that was originally formed by Clough and Duncan, and it can be found in the Foundation Engineering Handbook, which was a 1991 document edited by Y.H. Feng, and this is the second edition. So the idea here is basically to make things as simple as possible on our structural colleagues. So when we give them earth pressures to design for, it's actually not enough for us to just specify a resultant force, right? They're going to design, say that their job is to design the wall stem so that it can handle the flexural demands placed on it by the earth pressure distribution. Well, they actually need the full earth pressure distribution, or alternatively, they need to know the earth pressure resultant and the height at which it acts, and then they can compute the moment at the base of the wall. But if you want the whole moment distribution, you need to make an assumption about the distribution of pressures. It's not enough just to have the resultant force. So what we do in this table is represent the earth pressure as an equivalent fluid unit weight. And so maybe you've computed an active pressure resultant. Well, if you replace the soil with a fluid that has a certain unit weight and no shear strength at all, it would exert a pressure on the wall that's equal to the resultant that you computed for your active pressure. And so that earth pressure resultant is sometimes lighter than water, sometimes higher, sometimes more dense than water, but it's somewhere in that vicinity. And so this is kind of a very crude table. I think we can always do a better job than this table if we know something about the soil. So this is like the same sort of thing as presumptive bearing pressures in the design code for designing footings. If it was as simple as this table, there would be no need for geotechnical engineers at all. And so I don't think that's true. I think that geotechnical engineers can always do better than these sort of presumptive values. But if you're doing a very preliminary design or something like that, you know, structural engineers can use these to get a rough estimate for what the final number might be. But I would really discourage anybody from ever using this in final design. Okay, so anyway, the table is organized into this sort of hierarchical structure where you've got equivalent fluid unit weights and pressure coefficients. So there's two things. There's the equivalent unit weight, equivalent fluid unit weight, and then there's a K value. And that K value is basically how you multiply the surcharge load to get the equivalent horizontal pressure. So if you're designing for 100 kPa vertical surcharge, you would multiply, in this case, by 0.45 to get the horizontal surcharge acting on the wall. Then if you go down one level, we have level backfill. That's horizontal backfill here, and then this one is 2-to-1 slope backfill. It's pretty common for highway applications to have sloping backfill for grade separation and so forth. And then within each of those categories, we have at rest, which means no lateral strain at all. So they're making assumptions here about K naught. And then we have a condition where delta over H is 1/240, which is kind of moving toward an active condition. It's maybe not quite an active condition, but there is going to be some wall movement. So basically, when you're deciding which of these columns to use, you would have to know, is displacement tolerable in this application? Do we need to design for these higher at-rest pressures, or can we get away with designing for these lower sort of active-ish earth pressures that are associated with some displacement? Okay, and then within each of these, you've got the equivalent unit weight and the K factor, right? And then those are broken down into different soil types. So here we have loose sand or gravel, equivalent fluid unit weight is 55 pounds per cubic foot. Sorry for those of you who like SI units, this is in English units. The unit weight of water, just for reference, is 62.4 pounds per cubic foot. So 55 is less than water. It means that the pressure acting on the wall would be like if you filled the backfill with a fluid that's a bit less than water instead of the soil there. Then as the sand or gravel gets denser, the pressure goes down to 50, and then if it's dense, you'd get down to 45, right? Then when we get into compacted silt, it goes up, right? We get 60. Compacted lean clay, you get 70, and then compacted high plasticity clay, you're up to 80 pounds per cubic foot. And this is an interesting one because technically for clay, right after compaction, you can make a vertical cut in the clay and it's not going to push on the wall at all. So the horizontal pressure is generally potentially zero. But what they're acknowledging here is that clays will tend to creep over time and maybe go from an undrained to a drained condition and start pushing on the wall as consolidation happens or as swelling happens and the clay state changes. So if you are going to be supporting clay, you've got to be careful with shoring because it may change over time and go from basically zero pressure to something pretty high. And then you'll notice that the at-rest pressures here are quite a bit higher than the active pressures over here. So for example, for loose sand, instead of 55, you could design for 40 pounds per cubic foot. Significant reduction in the amount of pressure there. And then if you have sloping ground behind the wall, these pressure coefficients are all higher, right? And these are all active, right? Where we don't have passive equivalent unit weights. Usually it's only done for active. Although I actually have seen passive done for equivalent fluid pressures also. You end up with like, you know, hundreds of pounds per cubic foot sometimes as an equivalent fluid pressure, which seems a little funny, but if you actually are going to have an external force push on a wall and push it into the soil, a structural designer would need to know what that pressure distribution is and what the load is so that they can adequately design the wall to handle the loading conditions that are being imposed on it.